lectures on algebraic geometry and commutative algebra. At present, last couple of lectures we were studying localization of rings and modules, and today I will state a more general form of the universal property of the S inverse for modules, which is, and I will show you how useful it is to study homomorphism modules. So, let us start with as usual. So, this is the universal property of S inverse. I would just say this is more general than the previous one. Alright, so let me state precisely what it is. So, let phi from A to B be a ring homomorphism. In the previous version of the universal property, there was only one ring, but here now there is other ring B also, and S is a multiplicatively closed subset in A. Closed subset such that the image of S under phi are all units in B. This is the unit group of B. That means every element small s in S, image of that phi S should be a unit in B. So, further let V be an A module and W be a B module. And F is a homomorphism of A module homomorphism. A module homomorphism. Here we have considered W as A module also. So, W is an A module by restriction of scalars via phi. So, it is a module homomorphism. Then first of all, we can also consider then because we know there is a, so let me write a statement first, then W is also considered as S inverse A module by restriction of scalars using the ring homomorphism from S inverse A to B. This exists by the universal property of the S inverse for the rings. Okay, so this is not so serious statement. So I just put this in a bracket. Then there exists a unique S inverse A module homomorphism so V is here, W is here, this is a given A module homomorphism, and then we have S inverse V here, and this map is our iota V suffix S. Then we are saying that, let me use a different color, there exists a unique map here which I will denote S inverse F, and this should be S inverse A module homomorphism, S inverse A module homomorphism, such that this diagram is commutative, such that so the diagram is commutative means F, if you go by F, that is same thing as going from here to here, such that F equal to S inverse F composed with iota Vs. This is what we need to prove. But this is very simple. Okay, this is so that let me write here such that this diagram is commutative. That is this, that is such that these two maps are equal, F equal to this, and I want to describe its kernel, and kernel of S inverse F is precisely all those X over S such that X belong to the kernel of F and S is in S. Proof is very simple. I will just write the definition of S inverse F and leave the checking to check for you. It is very simple. So proof, we need to define. So define S inverse F. I want to define this map. So it should be a map from S inverse V to W. So it is defined on the fractions like this. This you define this to be equal to 1 over S Fx for all X over S in S inverse V. Now we have to check a number of things. I will just see that, check that S inverse F is well defined, that it does not depend on the representative of a equivalence class, and that S inverse F is S inverse A module homomorphism. And to checking the kernel, so further, if X over S in the kernel of S inverse F, that means what? That is S inverse F evaluated at X over S is 0, but this means, so that is, this is by definition was Fx over S is 0 in W, but W is a B module, and where this S in B is invertible, so that will imply Fx is 0, since S is a unit in B, image of S, so same as S. So that proves that the kernel of SF is precisely this, as you saw. So that proves this statement. This is more general than this. I will show you why it is more general, and we will give application of this to modules of homomorphism. So, first I want to write some remarks. So, remarks number 1, if in the above theorem V is an A algebra and W is a B algebra, and F is an A algebra homomorphism, then this map S inverse F is an S inverse A algebra homomorphism. That means it respects multiplication, but that is very clear from the definition of S inverse F, because F has that property. That was first remark. Second one, if in the above theorem V equal to W and F equal to identity map on V, then S inverse of IDV, this is a map from S inverse W to W is an isomorphism since iota WS from W to S inverse W is bijective. In particular, S inverse W can be canonically identified with W. So this one is very easy to check. It follows immediately from the definition of the map S inverse F we defined in the theorem. Now I want to give application of this theorem. So as an application, of the above theorem, we note the following. So let me repeat some of the assumptions. Okay, what are the assumptions? Let A be a ring. S contained in A be a multiplicatively closed set. And V and W, V W X be A modules the 3A modules, and for a homomorphism F from A module homomorphism from V to W, we know there exists unique S inverse F which is a homomorphism as S inverse A module from S inverse V to S inverse W. So, that means we have this diagram is commutative. This is what we proved in the earlier lecture, V to W, this given F. There is a iota map here, S inverse V. This is iota V suffix S. Similarly, there is a iota W, iota WS, and this is that map S inverse of F. So, this diagram is commutative. And we also saw that they satisfy the functorial properties, that is namely functorial properties. Once again I will repeat here, functorial properties, that is S inverse of IDV equal to ID S inverse of V, and if you have two homomorphisms G and F, so S inverse of G compose F is same as S inverse G compose S inverse F. This we saw last time, but it also follows from the earlier theorem. Further, now these are the functorial properties, but it satisfies some more properties. Further, if F prime is another homomorphism from V to W. Okay, so first of all, note that these homomorphisms, this is, so I will write here. So note that hom AVW VW is also an A module. And what are the operations here? Addition is, of course, if I have F and F prime, then this is defined by evaluated at any X. You evaluate individually and add them in W. So this is defined for every X in V. And what is the scalar multiplication? If I have A in A, then AF evaluated at X is you take Fx, this is in W, and use a scalar multiplication in A to define this. So this is also defined for every X in V. So with these operations, this becomes an A module. That is, now it is very easy to check that this is an A module with this addition and this scalar multiplication. These also can be seen directly because hom VW is a subset of W power V. See, W power V is the set of all maps from V to W, and that also has a structure of A module because you take any tuples which are indexed by the set V and terms in the module W, and then you can add component wise and you can scalar multiply component wise. This is also same as this operation. So in fact, this one is a submodule of this. Anyway, so we have this is also a module, and now the question is what happens to the sum of these homomorphisms, and when you apply S inverse. So, I am writing that first of all 0 map, the constant map 0 is also homomorphism. So, S inverse of 0 is 0, that is one. And if I have another homomorphism f prime, and if I take S inverse of f plus f prime, that is equal to S inverse f plus S inverse f prime. This is also very easy to check. You want to check these two maps are equal, just evaluate any x over s, and then you know this definition x over s. That means you have to evaluate f plus f prime at the numerator, and denominator is the same, and similarly here, and then you can just check. So, I will just say here check this, these equalities. Okay. So, what does this mean? I want to write this, the meaning of this. This is just a simple equalities, but this has bigger meaning, or at least important meaning. So, that means, this means the map, we have defined a map from where to where, from home A V W to home S inverse A, S inverse W to S inverse V to S inverse W. The map is any homomorphism F going to S inverse of F. But this is a module, this is also module, this is an A module, this is S inverse A module. So, this one is an A module, and this one is S inverse A module. So, I want to use the general universal property, that is why I stated in that general form. So, and hence the map is an A module homomorphism because we just now checked that the 0 goes to 0, the addition goes to the addition, that means it is an abelian group homomorphism, and scalar multiplication will come out. So, this is A linear map is obvious. So, this is an A module homomorphism, and therefore, by the above theorem, there exists a unique S inverse A module homomorphism from S inverse of this module, S inverse home A V W to home S inverse A, S inverse V, S inverse W. The unique one such that from here to here we have an iota map. See, I will use the different color. From here to here we have an iota map, iota, and now I will write only suffix s. I have to write here this module, that to S inverse, and then this, but this is same as this. So, this diagram should be commutative. So, you follow it by this, and then otherwise you go by that is commutative. So, there exists a unique homomorphism. If you give names, so if this is alpha and this is beta, such that iota composed with beta is same as alpha. Alpha equal to iota s composed with beta. Alright, so this map, there are interesting cases where this map is actually this map is bijective, but it is not always bijective. But there are some cases where this map is bijective, and some of these I will write as problems in the assignment sheets. Alright, so some more we already noted that S inverse preserves the exact sequences. So, that is, it maps exact sequences to exact sequences. So, I will also note one little bit more general than the last time. So note that this statement which will, so let F be an A module homomorphism from V to W. Then you can write down the exact sequence from this homomorphism. Then the sequence of A modules. Last time also we wrote one sequence, but that was not so useful. The one which I will write is much more useful. The sequence of A modules and A module homomorphisms. So, what is the sequence? 0, from this F we have a kernel of F, and kernel of F is a sub of V. So, from here to V there is a natural inclusion map, and from V to W this is given F. See, yesterday I removed W and wrote image of F, but now I want to keep that W. And where do I go further? To what is called co-kernel F, co-kernel F to 0. And what is co-kernel F is by definition W modulo image of F. This is the quotient module or residue class module of W by image of F. Now, I want to say that this sequence is exact, and hence we get an exact sequence of S inverse A modules and S inverse A module homomorphisms. So, before I write that sequence, I want to explain here why this sequence exact. So, we have to check exactness at these places. Exactness here is clear. So, I will write, we have to check here, but this is clear because here means this map is injective. This map is injective, that is because this is a natural inclusion. Here we have to check. So, what do we have to check here? We have to check that the kernel here equal to the image here, but this map is a natural inclusion map. So, the image is kernel F and the kernel F has also kernel F. So, this is also clear. Exactness here we have to check that this is the usual residue map pi. The kernel of pi we know, this is the residue class map from W to W modulo image of F. So, obviously kernel of pi is image of F. But this precisely means exactness here, and exactness here means this map, because 0 is here, this map should be surjective, but the residue class map is always surjective. So, this is also clear. So, therefore, this sequence is exact. Now, what is the sequence we will get? We will get a sequence when I apply S inverse to this. So, 0 S inverse of kernel of F to S inverse of V. This map is S inverse of this inclusion map. Then here the map S inverse F, this goes into S inverse V to S inverse W, and then the S inverse of pi map, which is S inverse of co-kernel of F to 0. But this S inverse of co-kernel of F is S inverse of W modulo image of F. And we saw in the last lecture that, okay, so in the last lecture we saw that the residue class map and the operation S inverse, they commute. So this is isomorphic to S inverse W mod S inverse of image of F. This is this. Similarly, we saw the kernel of this is also from this exactness you will know the image of this is precisely the kernel of this. So this is isomorphic to kernel of S inverse F. And similarly, this is also same as this is also isomorphic to, because this sequence is exact, the S inverse of co-kernel of S inverse of F. So in short, we have checked that the kernel and co-kernel, they commute with the operation S inverse. We have checked yesterday that S inverse and this residue class operation, they commute with each other, but kernel and co-kernel also commute this operation. Therefore, conclusion, also one more conclusion I write. Therefore, if S inverse, if F is injective, respectively surjective, then S inverse F is injective, respectively surjective. This means S inverse operation preserve the injectivity of maps and so preserve the surjectivity of maps. Alright, so okay, now I will make some observations about the chain conditions on the module. What happens to the chain conditions on the S inverse A modules? How to inherit them from the given module? So this I will do it after the break. Thank you.